We have the cardiovascular physiology discussion to get to still, so we'll do that here. One of the things that you should make sure you understand in terms of background is that blood pressure is highest in the arteries, lowest in the veins. It's pretty easy to remember that if you remember the simple fact that blood flows due to pressure differences. So the pressure in the arteries is greater than the pressure in the veins, which is greater than the pressure in the right atrium, at least at some point in time. The other thing to look at in terms of the pressure is in the heart we have systolic and diastolic pressure. So here's the peak pressure. That's when the heart's contracting. That's the systolic pressure. Down here we have the lowest pressure, close to zero for the heart, for all chambers of the heart, but that's the diastolic pressure. Within the arteries themselves, so this would be an example of the aorta, we have also systolic and diastolic, but notice the diastolic doesn't go down that much. The diastolic is there to maintain pressure to keep the blood flow going through the capillaries continuously. The difference between the systolic and the diastolic is called the pulse pressure, so you can see that here. And notice that the pulse pressure becomes less and less, and by the time we get to the capillaries, there's one continuous flow. So again, the key to, I think, a lot of the cardiovascular system is remember that blood flows due to pressure differences. So one of the pressures that we measured is called venous pressure. And the venous pressure is the pressure of the veins. That should be significantly lower than the pressure of the aorta because blood flows from the arterial side to the venous side, and the venous pressure is obviously by its name on the venous side, so it should have a fairly low pressure. So the way we did this is you could do it on laying on your back as well, but it's much easier to stand in the lab. Mark the height of the right atrium. You can estimate the height atrium with the third intercostal space, which is located about at the anterior axillary line. So a little crease in your front of your armpit, basically. So if you put a yardstick underneath the armpit and mark that, that's not a bad estimate of where the right atrium would be. So you hold your hand below the waist, and you do that to help with gravity. What's going to happen is blood is going to pool in your hand because of gravity, and as blood pools in your hand, your veins will distend. Then you'll slowly, with your arm next to the board, raise your hand slowly up. And as the hand gets higher and higher, the pressure of the column of blood in your hand, right, will eventually exceed the pressure of your venous system. So the pressure of the back of your hand will exceed that of the venous system, and blood will flow from the back of your hand to the venous system because blood flows due to pressure differences. So you look for the distended veins to collapse, and you mark that on the board, and you measure that difference, the difference between when the vein collapsed and where we had the right atrial height. So measure that difference, and then divide by 13.6. We divide by 13.6 because we normally measure pressures physiologically in millimeters of mercury. Occasionally we measure them, especially for some respiratory values, in centimeters of water, but usually it's millimeters of mercury. And so if we measure that difference between the vein collapse and the right atrium, right, so that's the VC minus RA here in millimeters, and divide by 13.6 to take into account the difference between the density of your blood and the density of mercury, because mercury is a very, very dense liquid, then that answer will come out to our venous pressure. We expect most people, their normally is 4 to 10 millimeters of mercury. 4 to 10 millimeters of mercury. Sometimes we see it in the lab a little higher because two things. One, students don't really want to commit to when that vein actually collapsed. So I think sometimes people move that hand higher up than they need to before they were stopped. And in addition, by the way we measure the right atrium with the basically using the armpit as a reference, is a little low. And so the right atrial pressure, right atrial height is low. So that difference is perhaps greater than it really is. And so sometimes we get people up even to 15, but 4 to 10 would be normal venous pressure. Right? So, just to make the calculation easy, we can kind of look at it this way. So let's say we measured that difference at 136. All right, so if the difference between where the right atrium was, our reference point, and when the vein collapse was 136, we would divide that by 13.6. And again, that's because we're taking the density difference between your blood and the density of mercury, and that would equal, and this is again 13.6 to get it into millimeters of mercury. This originally was in millimeters, right? So here's our distance in millimeters. When we do that, it's going to equal 10 mmHg, millimeters of mercury. Remember the chemical, the atomic symbol for mercury is Hg. So that would be right at the upper limit of normal. So really easy calculation. So that's what we did there. So now let's look at a different pressure, arterial blood pressure. So arterial blood pressure should be significantly higher than the venous pressure we just measured. When people say blood pressure, they invariably mean arterial, unless they're discussing something else. So the arterial blood pressure is estimated by sphygmomanometry. So it's an indirect measurement of not really ventricular pressure. It has to do with ventricular pressure. It's really arterial blood pressure. Because it's arterial blood pressure, we expect to have a systolic and diastolic pressure. We'll kind of talk about how to measure that in a second. There are other ways to measure blood pressure. You can measure directly. You can stick a catheter in some sort of artery of the body, send it up to whatever vessel you want to measure the pressure in, and let the vessel exert its pressure on the catheter and have a measuring device at the other end. But certainly, we don't have to do that every time we measure blood pressure. So the indirect method works pretty well. We're going to go over the manual method, although in the vast majority of clinical situations nowadays, they use an automatic blood pressure cuff. Okay? So it's an indirect measurement, though. We're going to basically listen. We'll kind of talk about what's happening. So what we're going to do is we're going to take a blood pressure cuff, okay, which is a sphygmomanometer, and we're going to basically pump it to different pressures. We're going to listen to blood flow as it moves across the cuff during systole and diastole. And then with a stethoscope, while we're listening, we'll go ahead and reference the numbers or for the sounds we hear, and then we'll measure the pressure. In a nutshell, the first sound we hear is called the systolic blood pressure, and the last sound we hear will be the diastolic blood pressure. When we report blood pressures, we measure them with systolic over diastolic by convention. And so, as an example, a normal blood pressure, which really nowadays it's not considered that normal anymore, would be 120, that would be systolic, and 80, that would be diastolic. Okay, so how this works, and this one actually shows it, and these all say kind of the same thing. But this one shows it, I think, pretty easily. So let's say somebody really did have a blood pressure of 120 over 80, and we wanted to measure that blood pressure the best we can. So what we're going to do is we're going to pump up the cuff above 120. We don't know it's 120. So usually you go about 150-ish. Okay? And once the cuff pressure gets above the systolic pressure, it completely occludes the artery. So notice the artery is pinched off right here, and there's no fresh blood, as indicated kind of by the pink-ish area here in the artery. There's no blood getting through. Because we have the stethoscope down here, so let me go back, the wrong button. So we would have the stethoscope right in here, okay? So this is what we would be measuring the stethoscope with. And what we're actually listening to is we're actually listening to the blood flow. Now, when we listen to the blood flow with the stethoscope, if we put it on normally without any cuff or anything, we don't hear anything. And that's because the blood flow has what's called laminar flow. And laminar flow is like smooth flow. And so the laminar just doesn't make a sound. And so you can't hear anything initially. So what we're trying to hear is we're trying to hear blood spurt through across the cuff. So when we have the cuff completely closing off the artery and we're listening to it downstream, so remember blood's going down this way. When we listen to it downstream, we don't hear anything because it's completely blocked up. It would be like damming a river. When you went on the downstream side of the dam, the water would disappear because there's no water coming through the dam. So anytime the blood pressure is above systolic pressure, that's what we're going to see. Okay, so we're going to see that. So then we're going to start with our pressure, as I said before, at about 150, and we're going to slowly let out the pressure of the cuff on the bulb to 2 to 4 millimeters per second. So not excessively fast and certainly not excessively slow. And eventually, when we get down to about 120, so when the cuff pressure gets to 120, now the cuff pressure and the pressure during systole of the artery are equal. And once that happens, blood starts to spurt, right? Every time the heart beats, blood starts to spurt through that area where the cuff is. It doesn't continuously flow because once we have systole, then we have diastole. And during diastole, let's say it is 80, like we see here, 120 over 80. When we see the diastolic pressure, the artery's back to being occluded and we're not going to hear anything. So we're looking at this blood pressure when the cuff pressure is the same or slightly lower than systolic pressure, we're going to hear the first sounds. We're going to hear that first sound. And it just literally sounds like your heart, because it is. You hear boom. It's a nice boom sound. Okay? And then as you continue to lower that cuff pressure down, about 2 to 4 millimeters per second, blood continues to spurt through the cuff. And so you'll hear a number of sounds that will be indicative of the heart beating. And that noise will get fainter and fainter. And the reason why it gets fainter is as cuff pressure decreases, blood starts to flow more freely, so that's what the second one is, through this artery. Once we get to the diastolic of 80, and the cuff pressure is 80, and the diastolic pressure of the artery is 80, then blood gets back to that laminar flow. And during laminar flow, remember we said earlier, you can't hear it. You can't hear it. So the sounds go away. So that's why we said the first sound is systolic. So let's say that first sound was heard at 120. And the last sound was 80. And that would give us a blood pressure of 120 over 80. So that's how it kind of works. You can take it, that's what we did here. You can take it step through here, kind of see how blood pressure goes. So that's measurement of arterial blood pressure. Now, here's just another way to look at it, and it's kind of the same idea. When the cuff pressure is higher than our systolic pressure, right, there's no blood going through. Once we get slightly below, we see a little bit of blood spurting through. That's this area right here. And as we continue to drop cuff pressure, we get more and more blood flow through until it's completely going through unimpeded. So that's another way to kind of explain it, but it's the same idea in terms of that. So we hear that turbulent blood flow. We don't hear the laminar blood flow, or we don't hear it when the blood flow is completely occluded. So one of the things that is important about pulse pressure is, one, it's a really easy indicator to calculate. Pulse pressure, which has the unfortunate scientific designation of PP, is a pretty easy calculation. It's the systolic blood pressure minus the diastolic blood pressure. So it's just the difference between the two. So again, if our blood pressure was 120/80, like we saw in the last slide, then we would say, okay, 120 minus 80 is 40. So the pulse pressure would be 40 millimeters of mercury. Pulse pressure is an indicator of stroke volume. So the higher the pulse pressure somebody has, the greater stroke volume they tend to have as well. And so you can't say, oh, their pulse pressure is 40, their stroke volume is 100. Can't do that, but certainly within an individual, it's a pretty good measurement. So if the pulse pressure goes down, that means the stroke volume typically goes down. So it's a nice indicator of that, and certainly is helpful in terms of calculation. So you should understand how to calculate pulse pressure, both in lecture and lab. The other thing that's important to measure in lab is the mean arterial blood pressure. Okay? So the mean arterial blood pressure is a couple different things that we need to kind of discuss. So first off, the mean arterial pressure is the average blood pressure, right? And here's the key, over time. All right, so this over time measurement is something we have to take into account. So it's nice to measure for a bunch of reasons, and probably one of the better ones is it's the homeostatically regulated variable that we use to keep blood pressure going. So it's the actual measured thing in our body. It makes sense to measure it clinically and have a measurement of that. And, it represents the driving pressure of blood. And if mean arterial pressure goes down, the driving pressure of blood goes down. It could certainly influence blood flow and things like that. So there's a number of different ways of calculating it. There's two ways if we have the actual blood pressure measurement. Okay. One way to do it, since it's the over time, is the heart spends about 1/3 of the time in systole at rest and about 2/3 of the time in diastole at rest. So if we take 1/3 of the systolic pressure and add it to 2/3 of the diastolic pressure, then we can calculate our mean arterial pressure. So if we take 1/3 of 120, that's 40. We take 2/3 of 80, that's 53.3, and we add these together, and that gives us a mean arterial pressure of 93.3. I don't like this measurement for a couple reasons. One, it's really easy to invert the systolic and diastolic pressure. That's one of the biggies. See students oftentimes making mistakes when they do 2/3 systolic, 1/3 diastolic. And also sometimes students have trouble on a calculator in class to figuring out how to take 2/3 of the diastolic pressure. I think a much easier measurement is the second one. The second one takes 1/3 of the pulse pressure. Remember, pulse pressure is the systolic minus the diastolic pressure. And then you just add that back to the diastolic. So a good check when you're done is your mean arterial pressure needs to be between systolic and diastolic. So if here's my systolic pressure and here's my diastolic pressure. It needs to be between those and about, well, not about, exactly 1/3 of the way. So it should be closer to the diastolic than the systolic, and it should be about 1/3 of the way between them. So that's like a good little check, but mathematically it comes out to this then. Again, if we took our 120 minus 80, kind of our basic blood pressure, we'll take that difference, which is 40, right? 1/3 of 40, I don't know why it's not on here, is 13.3. And 13.3 plus 80 is 93.3. It shouldn't matter how you take blood pressure. They both should give you the same answer. And to be honest, not a bad thing to do in an exam situation is to calculate them both if you have time and make sure you get the same answer. But I like this one better because you're only taking 1/3 of something. It's a smaller number. You're taking 1/3 of typically, so it's a little more manageable. And then you're adding it to 80. So I rarely see students ever crisscross these two when they always crisscross the other two. So that's what the mean arterial blood pressure would be. So looking at the next slide, again, kind of shows the drop in pressure over time, although unlike the first one we looked at, it doesn't show the pulse pressure here. And it again mentions that mean arterial pressure is a homeostatically regulated variable, and it represents the driving pressure of blood. One of the interesting things about mean arterial pressure is it tends to increase with age. And so we know in most people, mean arterial pressure rises as people get older. This is due to a number of different factors. Some of it is probably cardiovascular disease and narrowing of the arteries. Some of it has to do with other potential problems like diabetes and other conditions. It also has to do with loss of elasticity of the arteries as you get older. They don't become as flexible, as pliable as they were when they're younger. And that trend continues every decade of life until you get to about age 70. And once you get to about age 70, there's a significant drop-off in the average blood pressure. And the reason why, to be honest, is that most of the people that kept this pressure high in this region here have passed away. And so when they leave the pool of participants because they died from hypertension, then the average blood pressure actually drops back down again. So something to think about in terms of that and how important maintaining a proper blood pressure is for health, especially long term. So extended hypertension severely decreases life expectancy after age 70. So people who have high blood pressure in their 40s and never really get it fixed, by the time they get to 70, they're probably going to have heart disease and other problems, or certainly the potential is much higher for someone who doesn't have that problem. So that clinically is called hypertension. So hypertension is high blood pressure, and it does a number of things, one of which is increases the risk for cardiovascular disease. Recently, they changed the criteria for hypertension. Up until about 2 years ago, it was 140/90. Studies have shown that people who regulate their blood pressure at a lower value have what they call lower mortality. That means less people are dying, and lower morbidity. That means people are having less disease complications. So they've decided that the new normal is 130/80. So if you have a blood pressure that exceeds 130 in systolic or exceeds 80 in diastolic, then you would be said to be hypertense. One of the issues that you see is hypertension. You could have it in the systolic region. That would be called isolated systolic hypertension. There are reasons for that, and especially as you get older, that tends to increase the blood pressure with age, when the elasticity of the aorta especially is becoming less and less elastic as you get older. So that creates some issues. You could, for various reasons, have isolated diastolic hypertension, but more common is both. And so oftentimes, the question is, well, which one do we worry about most? Which blood pressure do we worry about being hypertense? And I think a lot of people realize that it's the diastolic region that is the one we worry more about. And there's a couple reasons for that. One is pretty simple. And if I said, okay, we're going to have to make you hypertense, we're going to have to give you hypertension, but we feel so bad about that we're going to allow you to pick which one you want. Do you want to be systolic hypertension or diastolic hypertension? And most people say, I would prefer to be systolic because I know it's not as bad. But a lot of times they're not really sure why. And even doctors and nurses sometimes don't have a really good explanation for this. Let me ask you the same question, a little differently though. I'm going to make you hypertense. Would you rather be hypertense 1/3 of the time or 2/3 of the time? And so since the heart only spends 1/3 of the time in systole and 2/3 of the time in diastole at rest, then being diastolic hypertension would mean that you're significantly longer time in the hypertense region. The other problem with that would be that's the pressure that the heart has to overcome to eject blood. And the higher that pressure is, that's the afterload basically pushing back on the heart, the harder it is to eject blood and the harder the heart has to work. And that's really the big reason why we worry about it. So both are troublesome, but certainly the diastolic region is considered much more dangerous. Now, when we look at, hypertension and again, the risk of cardiovascular disease, we'll see that as you increase your blood pressure, so here's your blood pressure readings down, that the relative risk of cardiovascular disease goes up and up and up. So someone who's got a blood pressure of like 200 over 120-ish, this big, huge blood pressure here, it's like, 20 times more likely to have cardiovascular disease than someone who had, a blood pressure of 110 over 70 or something. So, it does increase that risk. What causes hypertension? Well, one of the issues is that, hypertension is a couple things. One, it's called a lanthannic disease, lanthannic. And lanthannic is just a fancy way to say silent. So we don't know we have hypertension sometimes because if your body's regulating the set point for mean arterial pressure around a higher point, you're not going to know. So not only is it silent, though, in many cases it's called idiopathic. Idiot, right? Don't know. And pathic, place. So idiopathic is a fancy scientific name. And for those of you that have to take pathophysiology later in your studies, then you'll see this word a lot. We don't know what causes it. About 90% of hypertension cases are called idiopathic. Sometimes they use the word primary or essential hypertension. So primary hypertension, essential hypertension are also words we associate with that. And, oftentimes if you went to the doctors and said, oh, we're worried about your blood pressure, and you said, oh, what can I do? They'll give you this big, long list. And they'll say, have less stress, eat better, exercise better, lose weight, eat less salt, take up yoga or meditation, get a pet. Maybe if you're single, get married, or if you're married, get divorced, whatever is going to decrease the stress. But, the bottom line is we don't really know. We can't say, oh, for you, if you eat less salt, your blood pressure will go normal. But for you, if you exercise more, your blood pressure will go normal. It just depends on a lot of different factors. And that's part of the problem with an idiopathic disease. although we can regulate it fairly easily and inexpensively now with certain types of medication. The other type of hypertension is called secondary, and secondary means it's linked or caused by some other disease. And secondary hypertension comes primarily from a number of different cases, but one of the big ones is renal hypertension. So blood doesn't flow very well through the kidney, and that backs up. Even though we know what the cause of it is, you can't fix it very well. You literally need a new kidney, but if your kidney functions, you're not going to get a new kidney because someone else who's on dialysis needs that kidney much more than you do. So how does it, become dangerous, and what does it do? Well, one of the major problems you see with it is that high blood pressure damages arterial walls. And by damaging arterial walls, the first thing that we do when you have damage to an arterial wall is we start to deposit cholesterol plaque. So if you look right here, you'll see this is a normal artery on the bottom right. And underneath that, in the B1, which you can't read, would be one that's got a thrombus. And so if you see this little half moon shaped here, right, that's the plaque. And then this kind of ball sitting right in the middle would be the thrombus. Remember, thrombus is an stationary blood clot, right, in an unbroken blood vessel. So, and look at how narrow the lumen is, right? Just a little bit of blood's going to get through. Here's a normal artery, open and what they call patent, blood flowing through it. Other issues that come with hypertension is your baroreceptors adapt to the higher pressure. So they move the set point to a higher number, which isn't good. You also get what's called cardiac hypertrophy. So cardiac hypertrophy is an increase in muscle size. The problem with that is as the heart tries to eject the same amount of blood against a higher pressure, it has to work harder and it gets enlarged. And as it gets enlarged, it gets less efficient, which means it has to work harder, which means it has to get bigger to eject more blood, which means that now it gets even less efficient. And this gets into like this positive feedback cycle. It's not very quick, but your heart gets weaker, weaker, weaker over time. And that's called cardiomyopathy or heart failure. It causes fatigue, it causes a decrease in cardiac output. And one of the problems with cardiac hypertrophy is it's hard to distinguish between a positive cardiac hypertrophy. So as an example, before we had echocardiograms, which are basically sort of like sonograms of the heart, we had to rely on ECGs pretty much to see if your heart was enlarged. If you were a marathon runner or a soccer player or a cross-country skier or someone who did a lot of aerobic activity, then you could actually have cardiac hypertrophy. Your ventricle, especially your left ventricle, will be bigger than someone else's. But that's a bigger muscle size that comes from that positive exercise influence, as opposed to a bigger muscle size that's a disease process. And all we could tell in the old days was, yeah, your muscle's bigger, it could be a problem. But now with the advent of some modern tools like an echocardiogram, we can actually look at the chamber size and see what's happening, get a much better diagnostic view of that. But those are some of the effects of high blood pressure. Could you have low blood pressure? Yeah, that's called hypotension. And hypotension, most doctors won't give you numbers because if it's asymptomatic, the lower your blood pressure, the better. So asymptomatic means without, and then symptomatic symptoms. So if you press, though, most doctors say anything below 90/60 is probably pretty low. And what would happen is maybe if someone stood up abruptly or something like that, they got dizzy or fainted. So that's called orthostatic hypotension. We'll discuss that a little bit in lecture. So the next thing we want to look at is let's sort of look at what we do with the blood pressure measurements. Okay. So once we sort of figured out in lab how to take venous pressure, and we figured out in lab how to take arterial blood pressure. Then the idea was we'll take a subject, we'll have them sit quietly for about 2 minutes, and then take their blood pressure. And then they continue sitting. We get everything ready and get the pump up the cuff and get everything ready to measure. And then have the person stand abruptly and immediately, as fast as you can, take the blood pressure. So you've already got the cuff pumped up. You've already got the stethoscope in place. And you want to take it as fast as you can. Then you have the person remaining standing for about 2 minutes. Once they do that, the blood will start to pool in your legs. You'll get a change in blood pressure typically. And so take blood pressure and then have them recline, lay down, and see what the blood pressure is there. So we would measure it in systolic and diastolic. And it does create a little bit of a problem if you don't put in the mean arterial pressure. So here's the results where we have this subject that has different mean arterial pressure measurements. Okay, you can see them here under these different conditions. Okay, so notice the highest was standing and the lowest was reclining, and sitting quietly and standing abruptly were kind of right in the middle. So when you're quietly sitting, you have this resting sort of baseline mean arterial pressure intermediate measurement that we'll kind of use as reference. So what happens when you stand abruptly? Blood drops to the lower part of your body, and once it does that, because of gravity, there's a couple things that happen. One, because there's blood in your lower part of your body and there's not good venous return, you decrease that. So you get a decrease in venous return. Number two, since we're not returning blood to the heart, right, then we're going to have a less pumped out. So our stroke volume is going to go down initially. Okay? Since stroke volume goes down, we're going to decrease cardiac output. And since cardiac output goes down, and cardiac output and TPR are the two determinants of mean arterial pressure, then that's going to go down as well. So oftentimes we see a decrease in that initially when you stand abruptly. The problem is some people don't have a very fast reflex, so you don't see that. And the other problem is there's a compensation for that. Once your body sees that drop in blood pressure, it increases blood pressure above what you had, so it goes up. So it really depends on when you measure it, right? And people that do that might have orthostatic hypotension, which is a drop in blood pressure with a change in position. And that's because your baroreceptors aren't very active in this case. And not active enough to keep a baroreceptor reflex that keeps your blood pressure high, and certainly high enough to continue blood flow to the brain so that function would continue. So we're not going to worry too much about standing abruptly because it really matters when you catch that blood pressure, what's happening, and how fast the person responds based on health status. As an example, people that exercise a lot tend to have a very small baroreceptor reflex. And so, some people who do that might actually faint when they stand. So they don't do that too often. The next one I'll look at is standing. So if you look at the data for this person, we see after standing for 2 minutes, it has the highest mean arterial pressure, right? So 97.1. And if you think about it, when your body is standing straight up, then you have to exert blood in a much greater field against gravity because you got to pump blood to the upper part of your body, especially your brain. So your heart has to work harder, generate a higher pressure in order to get blood there. And by the same token, but reversed, reclining, lying down, right, after a couple minutes tends to have the lowest blood pressure. So you see here, it's significantly lower than the other ones. And that's because everything is in the same plane and the heart has to work less hard, right? It doesn't have to work as hard to pump blood to your brain now because you're basically in the same gravitational field as it, because it's even in terms of being on Earth. So before I get to Starling Forces, which we're not going to get to, I'll explain why. You should know how to do the arterial blood pressure and how to calculate pulse pressure and mean arterial pressure and which one we expect to be the highest and which one we expect to be the lowest. You should know how to calculate and interpret the venous pressure as well. You also should know how to do the Starling Forces. And this is a little one that kind of helps explain it, but this is one of the things you have to do on your own. And one of the reports I get back from students that move on to other programs often say, when we have our first test next week, and our teacher said, hey, there's a test next week, and that's all they told us. It's not, you don't need a Scantron, there's not this many questions, this many essay questions, study this. This is just, there's a test, show up. And so I think sometimes it's a good skill for you to develop how to do things on your own. And so this will be on the exam. There'll be at least a couple points on your lab quiz, your lab exam, whatever you want to call it, coming up. And you need to know how to do this. So, study yourself and try to figure it out. And there's a sheet in lab 21 at the very end that has answers posted that you should look at and make sure you understand how to do. So that's all I'm going to say about Starling Forces. And that's everything in this lab.